Okay, so obviously from calculus 1, before we start with calculus 2, make sure you know the basics, make sure you know all basic derivatives, and if just in case there are some hiccups on that, make sure you have tables of derivatives and antiderivatives with you just in case you forget or rule. So I'm not going to list all derivatives here, all basic derivatives, but obviously the ones that you will encounter more often, and I'm not going to write the trivial ones, but for example, the trigonometric derivatives, sine, cosine, and I can maybe write the let's see, the exponential, the easiest derivative rules, and so on. Natural log 1 over x, so on and so forth. So all the basic derivatives, and obviously correspondingly all the basic antiderivatives. So the integral of sine of x dx is minus cosine of x. The integral of cosine of x dx is sine of x plus a constant c, obviously, right? I mean, the antiderivative is not unique. It depends on a constant of integration. Obviously, the same thing for the exponential. These are the basic ones, and the reverse one for the natural log plus a constant c. When we talk about the differentiation rules, plenty of them, obviously. I mean, the well-known power rule, because this is used quite often in practice. So the derivative of x to the n, which is n x to the n minus 1, and then the corresponding power rule for the integral 1 over n plus 1 x to the n plus 1 if n is not equal to minus 1. Make sure you do not confuse the antiderivative of the power with the antiderivative of 1 over x. So when n is equal to minus 1, that's basically this case over here, the integral of 1 over x. So that's not going to be the power rule, obviously. Plus c here. One way to actually notice that you made a mistake if you use the power rule is that if you put minus 1 here, 1 over minus 1 plus 1 is 1 over 0, and that obviously doesn't make sense. So then we have the famous chain rule, which allows us to actually really differentiate lots of different functions besides the elementary ones, which states that the derivative over the composition of two functions is f prime of g of x, so the external function, so to speak, evaluated at the internal function, times g prime of x. Sometimes we'll have still troubles with rules like this, and this basically comes back to not understanding how the functions work and how composition works, or to be more precise, not understanding that functions really are rules, essentially. They are rules of an input, and then they give an output. We'll talk about that more when we review the basic, the substitution method. So as an example, right, if we differentiate, let's say, sine of natural log of x, assuming, of course, that x is positive, so that this is defined. This is the composition of sine and ln. So you can think of f to be sine of x, g to be ln of x. So we differentiate the external function sine, leaving the inside as it is, and then continue with the derivative of ln of x, which is 1 over x. Of course, at this point, you should do this quite quickly. If you cannot do it, you know, in a reasonable amount of time, so if you still feel shaky on what I just wrote right now, it's a very good idea to go over all these rules and really pay close attention to the first set of homework problems, because the first homework will be basically on this review stuff, just to make sure that everything is up to speed. Calculus 2 means application of integration primarily, at least in the beginning, the couple of first units. So for that, you need to handle very well all differentiation rules. One thing to keep in mind, so I think I'm going to move on to the next page with reviewing the U substitution and comment on that a little bit. In general, especially with the U substitution, because the U substitution actually, it's a rule that applies to composition of function as well. So again, make sure you understand what we mean by f of g of x, this composition of two functions, or how that looks in practice. So here's another example. Let's say you have to differentiate square root of x third plus sine of x. Again, let's assume that x is defined in such a way that this square root exists, because often there are conditions to be imposed on x. You cannot have, for instance, square root of a negative number. So again, get used to the idea of seeing this in terms of composition, right? So you have basically a function, an external function, which is square root of x, and the internal function, which is x third plus sine of x. So then you could view the square root of x squared plus x third plus sine of x as the composition of these two functions. You don't actually have to write them down like that. The idea is just to think in terms of composition of functions. So that means when I differentiate using the chain rule, obviously I have to differentiate the square root first, which this leads to the power rule. You may want to write the square root as a power. So we're going to use the power rule first, keeping the internal function as it is. So 1/2 x third plus sine of x to the power 1/2 minus 1. And then we're going to continue by multiplying with the derivative of the inside, which is 3x squared plus cosine of x. So of course, once you're done with the differentiation part, you can simplify as needed. I'm not going to bother with this right now. 1/2 minus 1 is minus 1/2. You can keep it like that. Sometimes in books you may see the answer given in form of a fraction, in the sense that the negative exponent is changed to positive exponent by flipping the inside of this parenthesis. So on the next page we're going to talk about the substitution method, and we're going to go over a couple of examples and some comments I want to make in terms of how you compute how you recognize when to use the U substitution, and how you deal with definite integrals using the U substitution. There's a discussion I want to make in terms of the bounds of integration. So stay tuned for the next page. So the substitution method was the last topic in Calculus 1. It's typically the last topic taught in Calculus 1. And this is a method of integrating the composition of two functions, because by applying the method, if it works, typically you should end up with an integral that is easier to solve, or that it's possible to solve, which otherwise wouldn't be possible. So let's review the method here. So in the formula, the way it's written states that the antiderivative of f of g of x times g prime of x dx can be written as the integral of f of u du, where u, hence the name U substitution, u is g of x, and of course du, which is the differential of u, will be g prime of x dx. So that's also learned from Calculus 1. If you remember, if u is a function of x, the change in u, or the differential in u, for a corresponding small change in x, is g prime of x dx. So whenever you have the stuff to integrate in this form, then this is suitable for the U substitution. It's called U substitution because typically we use U as the substituting variable, but you can use any variable really. I mean, you can call it Y substitution. You can decide to call g of x to be y, and then dy would be g prime of x dx, and then your integral to solve will be f of y dy. So there's nothing special about U, and often we use a different letter if U is used for a different purpose in the same problem. Now, the problem with formulas like this is that you need to go through lots of examples to see how they actually look like in reality, because this doesn't really look, I mean, doesn't really tell you how really the function to integrate looks like for actual functions, when you actually have actual functions instead of f of x and g of x. But notice that what the idea is that what you should see here is a composition of two functions in which you see in the same stuff to integrate both the internal function and the derivative of the internal function. So bearing a constant. It doesn't have to be that precise because, for example, if you have already g of x here and then on the outside you have not exactly g prime of x but g prime of x but multiplied by a different constant. So if you have essentially just g prime bearing a constant, the method still works because constants can be moved out of the integral and the method works. So the main idea, and let's write it as a remark here, the U substitution works, so the method works if you manage to replace all x's in u's, right? I mean, if you have all the variables that you had in terms of x, now in terms of u. So if you manage basically to cover everything in terms of the new variable. And of course, U substitution with a lot of practice can be recognized rather quickly. That's why it's one of the most used methods in calculus. I mean, it's one of the most widespread ones. Because it's kind of like a reverse of chain rule to an extent. So let's take an example, and let's start with one which is quite obvious in the sense that it really looks like the formula. So let's say I want to integrate sine of x to the power 3 times cosine of x dx. So if I see clearly here, if I look carefully here, I see a composition of two functions. So I could view this as the composition between a power function and sine of x, where the internal function is sine of x, and I see immediately on the outside the derivative of sine of x dx. So I see the differential of u on the outside of that composition. So composition of two functions, the derivative of the internal function of that composition times dx. So that covers everything, right? If I make this substitution, so I replace sine of x with u, cosine of x dx becomes du, then it's just a matter of using the power rule, 1/4 u to the 4, and then reverting back to the original substitution. So u is sine of x, and then plus the constant of integration. And that's your answer. As I said before, in practice, things don't look exactly like in the formula. So you have to be flexible here. So here's my next example. Let's say you have to find the antiderivative of 5x third square root of x fourth plus 1 dx. So what is the internal function? What's the external function for the substitution to work? So I have this square root of x fourth plus 1. If I differentiate, and we could do this in our mind, if I differentiate x fourth plus 1, I get 4x third. Now on the outside, and notice the outside of the composition, now it's in front of the composition. That's fine. The multiplication is commutative. I mean, this g prime of x doesn't have to sit attached to dx. It can be, to the left of the composition. But the problem is that, I mean, there's not a problem, but you may notice that the derivative being 4x third, what do I do with this 5? The answer is that you don't worry about it. If you basically get what you need on the outside, except a constant, a multiplicative constant, that multiplicative constant will not be your problem. It's just that you have to be careful how you do the algebra when you proceed with this substitution. What's important is the x third in relation to x fourth. The fact that x fourth prime is 4x third makes the substitution to work. So let's do the substitution. So u equals x fourth plus 1. Now notice the differential of u is 4x third dx. And as you notice, inside the integral, I'm going to have to replace x third dx, not 4x third dx. So just to make it clear, let's actually attach x third dx on the outside of that composition. So what I need from du, it's not just the whole thing, but just x third dx. So that means I'll have to move the 4 to the left side. So that means you divide by 4. So 1/4 du is x to dx, and this is the guy that basically is going to come here inside the integral. And of course, x4 plus 1 is going to be u. So now the integral is 5 square root of u 1 over 4 du. So now you notice why that constant, which was not the constant that we had before there, 5, doesn't really matter, because all constants multiplied by the function can be pulled out of the integral, and then it's just square root of u to be integrated. Write it as a power, and then use the power rule. Now, here's another little trick with the power rule. Remember, it's u to the 1/2 plus 1, 1 over 1/2 plus 1. So once you compute the exponent of u, which in this case is going to be 3 over 2, remember that whatever you get here, it should be the reciprocal of the exponent. So 1 over 1/2 plus 1 is going to be 2 over 3 anyway. So you could do that basically automatically. Once you compute the exponent, the reciprocal of it will be in front of it once you use the power rule. Let's do a little simplification here. 4 with 2, that's going to be 5 over 6, u to the 3 over 2. Revert back to the substitution, so that's going to be x4 plus 1 to the power of 3 over 2 plus a constant c. And we're going to do a couple of definite integrals on the last page. One thing I want to mention here, sometimes when the exponential is involved, in the beginning, people may have some confusions on whether the substitution works or not, simply because derivatives of exponentials kind of look like exponentials, because the exponential doesn't disappear completely, right? I mean, doesn't disappear at all if you differentiate it. So here's a typical example that sometimes is confusing. Is this suitable for a U substitution? It is, because if you think about it, if I differentiate the denominator, I'll get e to the x. So actually, e to the x together with dx is going to be my du if I replace u with e to the x plus 5. So, and then let's write it here. So du is just e to the x dx. So really, this is nothing but 1 over u du, right? If by u we mean the bottom of that fraction, if we mean e to the x plus 5. And of course, the integral is ln of u, which in turn is ln of e to the x plus 5 plus a constant c. So let's do a couple of examples with substitution involving definite integrals this time. And then I think that will be enough for our first lecture. So stay tuned for the last page. All right, so let's start with this example. The integral from 1 over 2 of x over 2 minus 2 over x dx. So there is one habit which I actually don't agree with. The habit is to not change the bounds of integration if you use U substitution. Now, this is not for U substitution, so let's just do this example, but then I'll go over one with U substitution to make the point about what I mean with this habit that I want you to not have, basically. So the idea is to, of course, find the antiderivative, and then at the end apply the fundamental theorem of calculus, or the Leibniz-Newton formula. Plug in 2, plug in 1, and then subtract. So in this particular case, things are not that difficult. It's a difference. So we have the antiderivative of x over 2, which is 1 over 2 outside, x squared over 2. And then minus 2, pull the constant out, the integral of 1 over x, which is natural log of absolute value of x. So with the Leibniz-Newton, remember, that means we plug in the bounds of integration and subtract. One very important habit to have in order to avoid computation mistake, it's a habit that I always have myself. Once you are preparing the Leibniz-Newton, so once you prepare to plug in the bounds of integration, start by writing 2 pairs of parentheses with minus between them. because that avoids any possible sign mistakes you may have, especially on the second part here when you subtract that parenthesis. So in the first, of course, parenthesis, plug in 2. So that's going to be 2 squared over 4 minus 2 ln of 2. And then minus parenthesis and then plug in 1, the other bound of integration. That's 1 squared over 4 minus 2 ln of 1. ln. And then you can simplify it. So that's going to be 4 over 4, which is 1, minus 2 ln of 2, minus 1 over 4. ln of 1 is 0, so that's going to be, that's it. That's going to be minus 0. 1 minus 1 over 4, that's 3 over 4, minus 2 ln of 2. Or if you want, you can bring the 2 inside the logarithm, and that's going to be 3 over 4 minus natural log of 4. All right, so this is an integral that we didn't need any method like substitution method. So let's do one for which the substitution is required. So let's say I want to integrate from 0 to pi over 6 the function sine of t. Let's use a different variable, sine of t over cosine squared of t dt. Okay, so here's the habit that I don't like. I don't like you to basically work through the substitution and keep the original bounds, because if the substitution is made, so if you go from one variable to another, stands the reason that the variable change. So in this case, t is between 0 and pi over 6. If the variable change, the bounds will change. So in this case, we're going to make the substitution for cosine of t, because we have sine of t dt on the outside. So we're going to do u equals cosine of t, du, the differential will be the derivative of cosine, which is minus sine of t dt. And now we have just an extra step to change the bounds of integration. So if t was 0, you look at the substitution and you say u will be cosine of 0, which is 1. So the corresponding lower bound for u will be 1. If t equals pi over 6, the corresponding upper bound for u will be cosine of pi over 6, which is 30 degrees, and that's going to be square root of 3 over 2. You could do this at the, if you don't change the bounds, you'll have to go back to the original variable when you're done. But if you change the bounds, you don't have to go back to the original variable. The reason I prefer this, and I think this is the way it should be, is because once you write the next integral in terms of u, it is actually incorrect to use all the old bounds. So let's actually make the substitution. Let's pay attention here. 1 over cosine squared becomes 1 over u squared. Sine of t dt, notice here, minus has to move over to the left of du, because we don't have any minus in the function to integrate. So that's going to be minus du, which you can move it out of the integral if you want. And then you can write 1 over u squared as u to the minus 2 in preparation for the power rule. Oh, I forgot the bounds, right? So the lower bound, as I said, is 1, and the upper bound is root 3 over 2. Lower bound is 1, upper bound is root 3 over 2. It doesn't have to be lower than, the lower bound doesn't have to be smaller in value than the upper bound. That's not important. And now we do the power rule, so minus u to the minus 2 plus 1, 1 over minus 2 plus 1, between 1 and root 3 over 2. Let's clean up a little bit these negatives, so that's going to be minus minus, u to the minus 1, which is 1 over u between root 3 over 2 and 1. So it's going to be 1 over root 3 over 2 minus 1 over 1. And so that's going to be in the end 2 over root 3 minus 1. So get into the habit to change the bounds of integration. If you don't change the bounds of integration, at this stage right here, when you're done with the integral, you'll basically go back to the original variable. You'll say the answer is 1 over cosine of t, and then you're going to plug in 0, in pi over 6. I want to point out that you will compute cosine of 0 and cosine of pi over 6 anyway at the end if you don't want to do them in the beginning. So there's no, it's not like you save any time if you don't change the bounds of integration. But by changing the bounds of integration, you move along from left to right, and you will have a correct integral in which the variable has the correct bounds. So always change the bounds of integration when you do the substitution. This will be even more important, as you will see when we move on to some fancier methods of substitution later, like the trigonometric substitution. So let's do another example like this, and then we could probably call it a day. So let's say we integrate from 1 to 2 the function e to the 1 over x squared dx. So here again, it might be a little bit tricky on what U substitution should be. Even if it's not obvious, give it a try, because sometimes you may have to actually proceed with the substitution to see if it really works or not. So u to the 1 over x is going to be the way to go. The reason is because du is going to be minus 1 over x squared dx. This is one derivative which is a power rule, but it's nice to memorize it actually in the fraction form, because it appears in that form often. If you don't know what I'm talking about here, well, you'll do an extra step. When I differentiate u, I differentiate x to the minus 1, right? So you write 1 over x as x to the minus 1, and then you differentiate with the power rule, and then that's going to be minus x to the negative 2. But the problem is, like I said before, in many books, in many exercises, the negative exponents are changed to positive exponents by flipping the fraction there, which is raised to the negative 2. So I hope now it's clear why e1 over x is related to minus 1 over x squared via the derivative. Don't forget to move the minus over to the left when you do the substitution, and of course let's do the bounds as well. So if x is equal to 1, u is 1 over 1, which is 1. When x is equal to 2, the upper bound, u is 1 over 2. And notice, as I mentioned before, the upper bound doesn't have to be larger in value than the smaller bound, but it's important to put them in the correct order. So when x was 1, u is 1. When x was 2, u is 1 over 2. Then we're going to have e to the u, and then 1 over x squared dx from du over here becomes minus du. Move the minus over to the left, and then the integral of e to the u is just e to the u between 1 and 1 over 2. Pairs of parentheses, minus e to the 1/2 minus e to the first. And now we simplify a little bit. Minus e to the first is e, minus e to the 1/2, or if you prefer, you can write it in terms of radicals like that. So that's it for our brief overview with calculus, and we're going to start over. Really, it's not, calculus 1 and 2 is really like a single course, essentially. So we basically continue where we left the discussion from calculus 1. So that's it for today. I'll see you next time.